So thank you, Derek, and good afternoon to you all. I was told there's no hard end time for this session, so in the next 2 or 3 hours, I hope to introduce you to some of the stuff we're doing at CERN, and the emphasis will be on the Higgs discovery, but also some of the physics behind that. So I'll spend maybe the first half or more actually discussing the ideas behind the fundamentals of particle physics and why the Higgs is an important component there, and then I'll talk a little bit more about the ATLAS experiment. Now, experimental particle physics is a big enterprise. The experiment I'm on is arguably the biggest scientific experiment in the world, and that's not just a physical statement, it's to do with the number of people. I share my papers with 3,000 co-authors. So the picture here, in case you're wondering, is to somewhat illustrate a metaphor for trying to find the Higgs boson. It was a very, very long slog. As I'll come to, it started in 1964 and came to its fruition in summer of 2012, probably, arguably. And you need an awful lot of people chained together to get there. Quite what this guy is doing, I don't know. I think he gave up and decided to do astrophysics or something. Anyway, that's very good. So I was also a little unclear as to exactly which level to pitch this. So given I know that we have some A-level students in the audience, I'm going to try and pitch it about that level. It may be a stretch a little bit for them. It may be a stretch for others in the room. But I find people prefer being stretched than talked down to. So I try not to talk down to people, but I hope it's comprehensible. And this is my view of what particle physics as a subject is all about. Essentially, we're trying to answer some very fundamental questions. We're trying to ask, what is it that matter is made up of? And what is it that holds it together? And I guess also, once you've found those bits, can you subdivide them further? I mean, this is a process that started way back in the time of the Greeks when there was a big argument about whether matter was infinitely divisible or whether there was a fundamental unit of matter. And it's atos, I think, is the Greek for that indivisible bit, and that's where we get the word atom, because for a while, back in the time of Dalton, people thought that that was the fundamental bit of matter and you couldn't subdivide it. But then we found that the atom was made up of electrons and protons and neutrons, and then subsequently we've discovered from the 60s and 70s onwards that those protons and neutrons are themselves made up of other things, quarks and gluons, which is about the level at which we're looking at stuff nowadays. And the question is, can you go further than that? I actually won't in this talk address that question any further. It's an interesting one. Our theories say you don't need to go any further, but we should be humble before the facts, and we should just keep on looking and making sure that really there isn't some hidden substructure below there. Some people believe that there is, and there are theories that follow that. So our aim is a unified description of the building blocks of matter and their interactions. Now, there is a consequence to that which ties the physics that I do with the physics that people at places like UCLan do in terms of cosmology. Because in the early phase of the universe was small and hot and dense. So there were high energies, there was a high density, high temperature, and the effects that shaped the universe in its very earliest phases are exactly those effects described by particle physics. And so you can argue that what we're doing at CERN is at some level experimental cosmology. We're not trying to make new universes, but we are exploring the physics that was at play in the early phases of the universe. So there's a fundamental idea in our description of the physics at the particle level, and that is the realization that the forces, the interactions that go on between particles, are mediated by the exchange of other particles. Now, at some level, this is a little linguistic trick. There are many ways you can describe the interactions, but what we find is that this simple picture of the exchange of particles corresponds to a mathematical description which does seem to explain what's going on. Now, people often ask me, if I give them an illustration like this little cartoon, two people on two boats, and they're exchanging a medicine ball between them, people can readily get the idea that if they exchange that medicine ball, it can push the two of them apart. That's kind of what you expect. What's also strange is by exchanging an object, you can pull the two things together. And they say, how is that? Well, frankly, in probably 20 years of trying to think of a publicly, generally understandable way of saying that, I cannot find a good physics example of that. The best that I can give you is a rather soppy metaphor. And the rather soppy metaphor is, if you and I exchange presents, it tends to pull us together. I'm afraid that quantum mechanics seems kind of soppy. It does that. So there are 4 fundamental forces that we know of. You could argue that if this was the 19th century, we'd be talking about exactly the same sort of physics, so they didn't know about, so much about the strong interaction in those days. But we would have said 5. We've already managed, even in the 19th century, to effectively unify 2 forces, those to do with electric charges and those to do with magnets. There was a realization through Maxwell and others that that's actually the manifestation, 2 different manifestations of the same effect. So we nowadays talk about the electromagnetic force. That's manifest all the way through modern life. It's there in lightning. It's there in if you rub a party balloon and hold it against the wall, it sticks to the wall for a while. You know about magnets. Then what other forces are there? Well, there's the strong force. And the strong force isn't just grim, like this nuclear detonation would suggest, but the strong force is actually what holds most fundamental particles, or what we used to call fundamental particles. Things like the proton and the neutron are held together by this thing called the strong force, because they're really made up of quarks, and they are bound together by the exchange of things called gluons, and the force that that describes is called the strong force. In fact, the first time that people encounter it, and the way you encounter it normally in school, is that you are told that it's the force that holds the nucleus of the atom together. So it's the force that acts between the protons and the neutrons to keep them bound together, because you know the protons are all positively charged, the neutrons have neutral electric charge. So if there was just electromagnetism, you'd expect them to fly apart, because like charges repel. But the strong force holds it together. Now actually that's just a little residue, a little leftover part of the strong force. The real strong force is much, much stronger and holds the protons and neutrons together. And for those, actually somebody was asking about van der Waals forces. It came up over lunch. If you know about van der Waals forces, the things that, molecular forces, the sort of thing that comes into play when you have something sticky and it sticks to another subject, another material, those are leftover bits of the electromagnetic forces that hold molecules together. Well, this is an analog of that is that stuff that binds the protons and the neutrons together is the leftover bit of the strong interaction that's holding the protons and neutrons together. Then there's the force of gravity down here. So the strong force, by the way, is much stronger than the electromagnetic force. That's obvious. It's holding those protons together. If it wasn't, they'd be flying apart. There's the gravitational force. You know about that. That's basically what's keeping the Earth orbiting around the Sun, or the Sun orbiting about the Earth, if you want to be truly relativistic about it. And is basically what dictates a lot of the large-scale structure of the universe, but that is actually by far the weakest of the forces that we know. It's important because it acts over very long ranges, so it has a universal effect. And because it acts on the mass of something, and we'll be coming back to this idea of mass, and there is only one mass, there isn't an anti-mass, because of that, it actually doesn't, you can't clump things together and cancel out their masses, and it acts over an infinitely long distance, so it in fact acts over the largest scales of the universes, and that's why it's really important for large-scale structure. But actually, it's much, much weaker than this force we have over here, called the weak force. The weak force you may have encountered through school or in your studies through something called beta decay, a type of radioactive decay. It's also actually vitally important to us because it's the weak force that is actually the important force in the nuclear fusion that powers the Sun, and so ultimately, effectively, is powering all life on Earth indirectly. So it's very important. It's much, much weaker than the strong force and much, much weaker than the electromagnetic force, but in fact is much, much stronger than gravitation. But in particle physics terms, it's the weakest of the forces. Gravity is so weak that when you start looking at subatomic particles, it really has no effect. And so we do not do experiments on gravity in particle physics experiments. It's when you put particle physics and other stuff together, like in the recent announcements of primordial ripples and the effect on the cosmic microwave background you may have heard in the last 10 days or so, that is the point at which gravity and the particle physics start to interact. And that's going on in the very early universe. What are the force carriers? Well, the electromagnetic force is carried takes place through the exchange of particles of light, the photon. So this gamma ray is an example of a photon, but we use the symbol gamma to indicate photons. So you have two charged particles here. They're exchanging a photon, which in the language of particle physics couples to the charge of the two particles. There are equivalent diagrams for the strong force. I already mentioned that things like the quarks bind themselves together by the exchange of particles called gluons. There are actually a whole set of these gluons. The particle physics language gets a little whimsical sometimes. We call the property that you're binding to here not charge, we call it color. The reason we call it color, I'll come back to in a minute. But there are actually a whole set of these gluons, and they hold the particles together there. In gravity, we've never seen direct evidence for the exchanged particle here, but there's lots of indirect evidence to believe that gravity is mediated by the exchange of a particle called a graviton. And we can say a lot of things about the properties of that particle, but I would not claim that we have any direct evidence for it. That is for the future, maybe a very far future, actually, if you want to do a particle physics experiment to prove it. And the weak interaction, well, here we have three different exchanged objects which are to do with the weak interaction. Two of them are called the W, and one has a positive electric charge and one has a negative electric charge. And then a little bit heavier than the W's, there are things, the thing called the Z0. Now, the Z0 is an interesting object. It's got a mass which is about 90 times the mass of a proton. Until recently, it was the most massive single particle that we'd ever observed in fundamental particle in particle physics experiments. The W's are a bit lighter. They're just below about 80 times the mass of the proton. But the Z turns out to be like a really heavy version of the photon. And it turns out that with our modern theories over the last 30 years or so, we have actually managed to continue this unification program, where nowadays in particle physics, we don't talk about the electromagnetic and the weak forces. We talk about the electroweak force, and that these two apparently different sorts of force are just different manifestations of the same underlying bit of physics. The thing that makes them really different is the fact that there is mass in these exchanged objects, a lot of it, and very little, no mass in the exchanged photon. And because of that, it seems that the weak interaction is weak, and it seems that the electromagnetic interaction is a lot stronger. If you want to come back and ask me about that at the end, I think that's probably where I should answer and think more on that one. But it's not hard to explain why that might be if somebody wants to ask me later on. So I like to throw in an idea for people to take away when I give a talk like this. And one of the important ideas I like to bring in this one is the idea of symmetry. So through most of science, and certainly through physics, a lot of what we do is related to ideas of symmetries. You look at the symmetry of the problem that you have, you look at the evidence you have and look for patterns and symmetries. And from those patterns and symmetries, you can infer something about the physics theory, the physics description that you want to write down. The mathematics should reflect the symmetries of the mathematics will reflect the symmetries of the actual physical situations that you see. And in fact, Emmy Noether, back at, I think, beginning of the 20th century, wrote something very powerful called the Noether theorem. I'm sort of like championing unknown women in science, and Emmy Noether should, I think, be much, much better known. But she put together this theorem that said that if you have a conserved quantity, there should be an associated symmetry with it that in the jargon guards that conserved quantity. So there are some examples of this. If you look at the idea of momentum, I hope everybody's got some idea of what momentum is. It's a combination of the mass times the velocity, the speed of an object. If that momentum in a system is conserved, that's associated with the system essentially being unchanged if you just displace it in a straight line in one direction or another. It's a translational symmetry. Similarly, if your system is essentially unchanged if you displace it in time, that's associated with the conservation of energy. And then you can look at a rotational version of the first one. If instead, if you take the system and you rotate it and it's essentially the same, then you will have conserved angular momentum, if you know what angular momentum is. And there are other symmetries to do with the electromagnetic fields which are associated with the conservation of charge. And then there are other examples of this in relativity. There are the symmetries of space-time, give you energy momentum conservation, and so on. So this is really powerful, and it's particularly evident in particle physics, because the way we write down our theories and the things we then try to test are all usually based about identifying the underlying symmetry of the interaction that you're studying. So there are a special sort of symmetry in particle physics, they're called local symmetries, and the examples of this, if you're looking at electromagnetism, that's associated with a symmetry which in mathematical terms, in group theory terms, is called U1. It's unitary order 1 symmetry. That is the symmetry that describes rotations, how all the symmetries are generated when you rotate an object. And that corresponds to the theory of the electromagnetic interaction, quantum electrodynamics. If you look at the weak interaction, then we see a symmetry which is somehow related actually to the rotation symmetries. It's called special unitary order 2 symmetry. You will have encountered something which has this symmetry, I think. Most people here have done science at some level, and you probably encountered the idea of spin. And you know that, for instance, when you pack electrons into orbitals around an atom, there are only certain allowed arrangements that you can put, and it tells you how you can couple something which is either spinning upwards or spinning downwards, but in quantum mechanics it can't really be spinning sideways, it's one way or the other. That combination of the two states, that corresponds to the 2 in SU2, effectively, that algebra, that mathematics, that symmetry is an SU2 symmetry. And it's not spin itself, but there's a related spin-like object which is actually describing the weak interactions. So SU2 describes the weak interactions. You take the same algebra, and instead of just having 2 states, you allow there to be not a spin up, spin down. You can combine 3 different states. That generates a thing called SU3. Now, our theory of the strong interaction, which we call quantum chromodynamics, and I mentioned before this idea of a charge we call color to do with the strong interaction. With colors, you have 3 primary colors, red, blue, green, or depending on how you want to do this, there's printing colors and optical colors, but there's 3 base colors, and you can combine those colors to give all of the other colors. There are 3 charges associated with the strong interaction. You combine them, and you can generate all of the possible colors. That is essentially the extension of a spin-like symmetry to 3 different colors. You get this SU3, and that describes the strong interaction. For gravity, we do have theory about how this works. Less detailed is how you apply this in a quantum mechanical sense, but the symmetries, the inner symmetries of the coordinate system are associated with gravity. So all of those forces you can associate with symmetries. So you have some nice simple solution, and there it is. That is the that is the theory of the electromagnetic weak and strong interaction. It's not including gravity there. I can't do everything in one slide. Come on, what are you expecting? But it's beautifully simple. I mean, you could solve that, couldn't you? Well, did I say simple? It's not that simple, but it is actually fundamentally, because what that is just combining 3 very simple symmetry groups. The symmetry of the SU3 of the 3 colors, the SU2 of the 2 isospin states, they're called weak isospin states, and the U1 of electromagnetism. So it's actually for underlying the ideas are very simple. And you can put those together with the bits that we've discovered that seem to be fundamental. This is essentially all of the bits of our understanding of elementary particle physics. There are the quarks. There are the up quark and the down quark. Couple up quarks together, put two ups and a down together, you get a proton. Put two downs and an up together, you get a neutron. And what else do we need? Well, to make an atom, you know you need electrons, so here's an electron. This is a type of particle called a lepton. And there's the electron. But it turns out that's not enough. We discovered in the first half of the 20th century that there has to be another particle, which took a lot of discovering, but was discovered. And that's a thing called a neutrino, which you may have heard of. So this is the electron neutrino. So fine, we've got these 4 bits. What more do you need? Well, actually, it turns out that all of these things have heavier siblings. There's the charm quark and the strange quark. And there's a bigger, more massive version of the electron called the muon. And the muon has an associated neutrino, the muon neutrino. And it doesn't stop there. We've actually found that there are 3 generations of leptons. There's the tau neutrino, beauty or bottom quarks, and top quarks. I like these a lot, actually. A lot of what I do in my day-to-day life is to do with beauty. I like looking at beauty. It's great. I have a whole other talk on that one, if you want. But then to make these things interact, you have these different force carriers, the two W's, the charged W's, the neutral Z, the gluons, and the photon. And that's it. We have a beautiful theory, we have all the mathematics, it all works, it incredibly well matches all of the observations that we've made over a period of 30 years. It's great. Apart from one slightly embarrassing point, and it's this table. This table has got the 3 generations again, and this scale here is a scale of masses. In fact, it's a logarithmic scale, and there's a big break, in fact, in that logarithmic scale here. So these are things with absolutely tiny masses, electron neutrino, muon neutrino, tau neutrino. Strictly speaking, we don't know the order of those masses, but it's widely believed they're probably in about that order. But we do know that they have masses, and we do know that they're different. Then we got these light things, the up and the down and the electron. Then their heavier versions, the charm, the strange, the muon. And then even heavier stuff, the tau, the bottom, and the top. And the top quark actually is really massive. I said the Z is the most massive particle we know until recently. The top quark actually has a mass which is double the mass of a Z boson, but the top quark, and in fact none of the quarks, can appear on their own. You can't pull them out of other particles. It's something to do with the nature of the strong interaction. They always come coupled with another quark. So it's not a standalone particle, but it's really massive. And then you've got the force carriers, the W's, the Z's, and this little thing we'll come back to, the Higgs. It's not actually a force carrier, but it is a boson, and the massless particles. The problem is, all of that beautiful theory, all of that great agreement to an incredible degree of accuracy. I mean, the mass of the Z is probably the most precisely measured fundamental parameter in physics. All of that fails completely as soon as you introduce a mass to the particle, because it breaks the symmetries. And in fact, in physics, at least, and quite often in chemistry and other things, it's the way the symmetries break is almost as important as the symmetries themselves. And that's a really embarrassing problem. So here I just said that. So how do you fix it? Well, it's tough. But in the early 60s, about 1964, a group of theorists, in fact, a couple of groups of theorists, thought about the problem. And they proposed a way of effectively having your cake and eating it. They came up with what we nowadays call the Higgs mechanism, which is beautiful and elegant, but frankly, until you had evidence for it, seemed a little contrived. But Peter said, well, you should be able to find evidence for it, because if this Higgs mechanism is there, then the experimental evidence would be that there should be a new particle called the Higgs boson. And it's for that name that Peter's name is truly associated with this, and the Higgs boson really is Peter's. Because other people may have thought, well, it's obvious it should be there, but they didn't write it in the papers, and that's what counts in science. Okay. So like I say, breaking symmetries is very important too. I can give you an example of breaking a symmetry. Imagine that you've got a ball balanced on the top of a little hill. That's a nice, beautifully symmetric situation. It's not preferring any different direction at all. But you can have a small perturbation, a little gust of wind or whatever, a little tremor in the earth, this ball will cease to be in its symmetric state and will roll down. And when it rolls down, it will roll down in one particular direction. And it will break the symmetries. It will say, I'm picking out one direction in space. Okay? And there are lots of examples of this. Another example you might think about is what happens with water when it cools. Water is actually a very highly symmetric state. The molecules are rattling around in all sorts of different directions, and there's no one preferred direction. As you cool it down, what happens? Well, it freezes. It freezes to ice. And you know that ice tends to be crystalline, so it has very definite preferred directions compared to the water state. So there's a much lower degree of, for all you might think of ice crystals as being beautifully symmetric, there's a lot less symmetry in the ice than there was in the original water that the ice froze out of. Okay, there's an analogy to that. In some sense, the Higgs mechanism says that all of the masses of the fundamental particles were set when an underlying symmetry was broken in the early phases of the universe as the universe cooled. And at high energies or temperatures, we expect that that symmetry would be restored, and at the point at which you can effectively treat the particles as massless. Now, I'm going to try and do a little illustration of the mechanism in a minute. So I'm going to have to pick a victim because I need somebody to, A, confirm. Does anybody want to be my beautiful assistant? Would you want to be my beautiful assistant in a minute? If you just get ready, we don't need to do it just yet. I'm going to give you an example of this, how the mechanism works. So this is an old set of slides which have been around for a while. So you'll notice there are quite a few names associated with the Higgs mechanism now. We try to be terribly politically correct because not all of them got the Nobel Prize. So the Higgs, Borut, Englert, Hagen, Gernick, Kibble mechanism. Higgs was doing it, Borut and Englert were doing it. Unfortunately, one of those died before the Nobel Prize was awarded, but two of these guys got the Nobel Prize last year. And then there's another group here led by Tom Kibble, which were producing papers about 2 months afterwards. Unfortunately, they don't give silver medals in the Nobel Prize, so they didn't get it. There was a little bit of rancor about that one, but you can't have more than 3 either. So which of those 3 would they have picked? They're all alive. Anyway. This is the analogy of how the Higgs mechanism works. The idea of the Higgs mechanism is the particles, in essence, are massless. So the theory works. But some of the fundamental particles acquire a mass. How do they acquire a mass? Well, the universe is supposedly filled with what's called a scalar field, but a field with which all of the particles can interact. An analogy for that might be this group of people who are sitting there milling around at some rather dull-looking drinks party, and then into the room walks a stereotypical dead white male physicist, and people think, oh my God, you're dead, this is interesting. And not surprisingly, there's a bit of excitement, and people cluster around him. Now, initially, that physicist could move quite freely until anybody noticed them. But by interacting with all the people around, that physicist suddenly found it rather hard to move. Now, what do we mean by a mass? Well, there are a couple of answers to that question, but the original one goes all the way back to Galileo. And the original answer Galileo would have given would be, well, he wouldn't talk about forces, actually, because that language came about couple of decades afterwards, but if I apply a certain force to something, if it has a low mass, it will accelerate a lot. If it's got a high mass, it will accelerate a lot less. So, you know, I take my nephew and put them on, nephews and put them on a skateboard and I push them, I can push them quite quickly. If I stand on the skateboard and they try and push me, even if they had the same force, they wouldn't get me going half as fast because I've got a lot more mass than they have. So what's happening here? You have something that apparently was moving freely, but by interacting with the field around it, it appeared to acquire more inertia, it appeared to be more massive. And this is the fundamental underlying idea of the Higgs mechanism. Where does the boson come into this? Well, imagine we're back with the original dinner party, and this is actually full of, you know, science nerds, and somebody spreads a rumor. Hey, ATLAS think they found the Higgs boson. What happens? Well, a group of people start talking, and they're talking and talking, and they cluster together, and they would find it very difficult to move around the room, not that they'd want to particularly. So you see that the field itself can clump together, and it apparently acquires a mass. That is the analog of the Higgs boson. The Higgs boson is the quantum of that field. It's something made out of the field itself. I'm going to give a little other example of this. So this is, would you mind? I'm sorry, I'm sexist like that. I have to pick a victim, and he invited me, so I can't ask him. I could ask you if you want. Would you mind, just for a second?
Oh, coming out.
Just a mind, yeah.
I use a stick actually.
So in which case, I'm sorry. In which case, would you mind? You can. I have a different beautiful assistant. Okay, I'm going to have to switch this mode. 1 second. Oh, here we go. Switch to visualizer. Hopefully this works. I have here. Sorry.
Press the lamp button.
Oh, sorry. Yes. The power one.
Lamp.
Yeah. Oh, yes. There we go. You wouldn't believe I'm an expert. It was on.
There you go.
There we go. Oh, yes. I have in my hand. This sounds very wrong. I have in my hand 2 balls. Will you attest that they are essentially the same? They're the same size, they're silver, they weigh essentially the same. Mm-hmm. Okay? So you would believe that these 2 things, which essentially, I mean, they're very light actually, they've almost got no mass. Would you be prepared to just try and catch something for me? If you just put your hand over to one side here, because this can go quite quickly. I'm going to...
Oh, I see here.
Yeah, just here. It's not going to rocket off the end. It's just if it drops off.
All right.
I don't want to lose these things. They cost a bit. This, I'm going to roll down the plate. It's on a slight incline. Sorry, you probably can't see it so well, but it's on an incline. It's going to roll down, so there's a fixed force going to be applied to it by gravity, and you'll see it will accelerate. So this thing, if I put it on here, I believe it's going to go quite quickly. Yep. Pretty fast. Okay? The other ball, here, same size, apparently almost massless, the same thing. Do the same thing here. Careful, catch it, oh. It's a bit of a trick, but this is an analog. There are eddy currents being generated as this thing rolls down. There's a magnetic interaction. This thing is interacting with the field. It's then apparently slowing down because of that interaction. It's a little analogy for what's supposed to happen with the particles as they move through the Higgs field. Okay, thank you very much. It can be quite a lot more exciting actually if I do it running down this tube, because you're never quite sure when the ball's going to shoot out. And, good, I'll switch back. Speak to me. Okay, good. Right, so this means we need to add something to our picture. We need to have the Higgs boson added to our set of particles if this theory is going to really stand up. And it has some other nice properties. These diagrams down here are called Feynman diagrams, but they also show, we don't go into the details, there's another fundamental problem actually in the theory, which it would claim that there are some interactions which at not ridiculously high energies would have a probability of happening that is greater than 1, which is kind of embarrassing in a theory. Putting the Higgs in, these diagrams cancel this diagram, and you keep a nice finite probability. So we have a Higgs to look for. So we said, great, we'll go and look for it. I'm an experimentalist. You can do all your fancy theory you like. I don't believe it unless I can find something. So we went looking. So we said, right, where should we look? Well, it'll decay in lots of different ways. These are the way it will decay. That's nice, so we know what sort of signatures to look for. So how heavy is it? The theory doesn't tell you how massive the Higgs should be. It can put some limits on it. It couldn't be incredibly massive. But the not incredibly massive means not more than about beyond the limit of the current LHC search. We then have lots of other indirect evidence which restricted the Higgs mass a bit further, or the theory would be inconsistent, but it didn't tell us where to look. So people started looking, and they started looking in 65, 66, and 67, and 68, and 69, and several generations of accelerator. I've worked on 2 full generations of accelerator that were looking for the Higgs. And I'm pleased to say I was still alive and working when we actually found it, because from 64 through to 2012, we found it. Actually, I'll skip this one. This is just showing how beautiful all the agreement is from with that theory. but we took a long time to show whether the Higgs boson actually existed. So this is the place where we finally trapped the thing. So this is a picture of the basin around Geneva. Geneva is in this area at the end of Lake Geneva here. It's not the most distinct picture ever. You can see the Alps in the background. The highest peak back here is Mont Blanc. On this side, actually, there are also mountains called the Jura. And this red line marks the path of our accelerator. Actually, it's the same path as the previous generation of accelerator, which was called the Large Electron Positron Collider, which I also worked on. But we replaced that with a new collider called the Large Hadron Collider. And it goes from about 150 meters underground here to 50 meters underground here. It's not that we built it on some ridiculously big tilt. It's because the ground here is rising. Actually, it is on a tilt. It tilts about 1 degree that way. You can think about that one for the end as to why we did build it on a small tilt. The main CERN site is kind of a triangular smudge here, so my office is over there, and my flat is just in a nice little village here. If you're ever passing by, we can have a cup of tea. The experiment that I work on is at this place here, ATLAS. There is a sister experiment over here called CMS. Both experiments actually discovered the Higgs at about the same time. We had a stronger signal, but there you go. Those are the brakes, guys. So in that accelerator, we accelerate protons and collide them with protons. The energy in the beam is quite immense. In a given time, the beam energy is 362 megajoules. So I like to try and think of analogues for these things. So I started off with something a bit militaristic, which is one of our last remaining aircraft carriers. So HMS Invincible, HMS Maritime Quest, weigh about 20,000 metric tons. So you take that energy, put it into that object. It's equivalent of this traveling at about 13.5 miles per hour, which doesn't quite sound as impressive as you'd hope. You then think of something nearby to CERN, like the French TGV. That weighs about 400 tons, so it's the equivalent of this thing moving at about 93 miles per hour. The one I liked, though, was if you take an unladen Routemaster bus, which weighs about 7 tons, it would be traveling at about 200 kilometers an hour. So basically, it's the night bus in Harry Potter. So we take those beams and we collide them. And this is a nice French-related cartoon for this. The program we're doing here, I mean, if you know a bit about particle physics, this probably is a bit talking down, but it isn't such a strange idea that you try and understand what's going on by scattering one particle off another. I mean, at the moment, you're doing something similar. You're learning about what's going on. What I'm doing, you're learning about what's going on that screen through a scattering experiment. Light is scattering off objects. You're then detecting them, and you're inferring what's going on around you by the scattering of particles off other objects. We do the same sort of thing, though, as I think it was Rutherford who said we're doing it a little bit more crudely, because he gave the analogy that what we're trying to do is the equivalent of firing an artillery shell at a pocket watch and trying to infer how the pocket watch works from the bits that fly out. There is another reason why we're so brutal, though. You want something really high energy as your probe for a rather simple reason. This applies to light as well. There's a wavelength associated with light. If you want to see structure on a very small level, that wavelength of the light needs to be comparable or smaller than the size of the structure that you're trying to see. And you get the smaller wavelength by putting more energy into the light. Through quantum mechanical effect called the de Broglie relationship, it's also true that matter has an associated wavelength. And to have a small wavelength on your matter, you need to have a very high momentum for those matter particles, so you have to have very high energy beams. So that's one of the reasons why we go and build our big toys. It's not just because we like big stuff, and we're not all men, it's not a size thing. It's actually because you need it to be able to resolve very small structures. And we're really not all men, by the way. I'm quite pleased with the gender profile in ATLAS. It's getting pretty balanced nowadays. And we've had, of course, at the time of the discovery, we had a female spokesperson, which, you know, Fabiola is one of the best physicists I've ever met in my life. She's a very formidable person. So we've had good times. This is the 10th of September 2008 when we actually turned on the beams. We saw the first collisions. Of quite a few of my friends in here, some people from not far from here, actually. Steve, like myself, is from just down the road in Liverpool originally. Unfortunately, I was stuck 2 floors above in another control room, actually trying to make everything work. But, you know, we were still all pretty excited. Unfortunately, 9 days later, and I was still on shift, they really should have given me a break, we had a bit of a mishap. You probably heard about this in the news. This whole accelerator, to save on energy, uses huge superconducting magnets. So we have large superconducting systems which are chilled almost down to absolute zero. Each octant, each eighth of the accelerator, is the largest superconducting system in the world. And unfortunately, you need superconducting cable, which you can't make in hundreds of kilometers continuous length, so you have to solder them together. It turned out that even though we thought micro-ohm resistances were tolerable, it seemed that there wasn't quite good enough solder in one of those joints. It went ohmic, became resistive, and you put currents through a resistor, you generate heat, so the stuff around it also became ohmic and resistive, and you had a whole huge current going through a very small space, so it vaporized, which in itself would have been unfortunate but tolerable. Unfortunately, it then vaporized the cable and started arcing, and it arced to a nearby baffle, which was metal. Unfortunately, that baffle was the containment for some of the liquid helium. It punched a hole in, and this is in a confined little tunnel underground. All of a sudden, many tons of liquid helium vaporized in a really small space, and it was like a rifle firing. So there was a huge shock wave went down the section. The thing is divided up into sectors. The first sector, we had trips on all the magnets and huge disruption. It blew the doors off. Yes, you can do your Michael Caine impersonations if you want, and actually disrupted the next sector. And we lost about 100 magnets in that one incident. There were these things, this is one of the dipoles, it weighs about 7.5 tons. It got displaced by something like a meter and a half. I mean, that's showing you how much power there was in these things. And it really was very, very nasty. So we went back, we put in even better safety systems, did even more careful checks, and we returned with the beam in 2009, and we've been running ever since, up until the end of last year. We'll talk about the future right at the end. But we took a lot of data between 2009 and 2012. Just to say a little bit about the ATLAS experiment, which is the one I work in. This is a slightly old picture. I think we're currently in 46 different countries. We are definitely in all 6 of the major inhabited continents. We'd love to get somebody from Antarctica in, just to be able to say. Actually, the computing stuff that I work on with this does link in IceCube, which is in Antarctica. So we actually have the computer system running in all 7 continents. We have, as I say, about 3,000 collaborators. The experiment itself is big physically as well as in terms of the number of people. This is the surface building where both ATLAS and CMS have their offices. Mine's around the side on the 4th floor there. This is the size that the detector would be if we put it in the middle bit of the building. So this is 5 stories high. The detector itself would be a bit more than 5 stories high. This is a graphic, a cutaway graphic of the whole detector. It's got lots of different layers. In the middle, there's the bits that actually track where charged particles go. A lot of this is magnets. The reason you've got magnets there is you want the charged particles to bend, because the amount they bend tells you essentially how fast they're going, so you can work out the momentum of those charged particles. We have other detectors which measure the energy of those particles. If you can measure their energy and you measure their momentum, you can work out what the particle masses are. And we have other systems at the outside detecting some different sorts of particles like muons and so on. Lancaster, in fact, was involved, and Liverpool and Manchester were involved in building these bits here and here. So big, huge detector. We were building bits that you can actually pick up. The inner tracker is sort of about that big, and we built the forward wheels of that, and we're working on the upgrade of that at the moment. So you can see what we call the Géant standard man and the Géant standard woman standing here and rather precariously up here. This is a big detector. And the beams go in either end and collide in the center. Okay, so we started getting our first results from the LHC, and the first thing you need to do is establish your own credibility. You need to find things that you know are already there and show that you can measure them really, really precisely. So we discovered a lot of the old friends, like the W boson and the Z boson that I mentioned before, and the top quark. And we now are making really competitive measurements on the properties of those objects, which rival things from previous generations, and we're going beyond what could be done before. There are things we call standard candles. So in the B physics, for instance, we do a lot of stuff, and there's a particle called the J psi, which is actually made up of charm quarks. These are really important for making measurements of antimatter, which is the subject of a whole other talk you could get me to do sometime. They're really interesting for the physics, but they're vital, measuring these things, to understand that you really have your detector perfectly calibrated, that you can really believe the measurements that you make with the detector. And it's tough. This is by no means the most difficult situation we deal with. When the beams go through each other, it's not just one proton collides with another. We actually, at the end of our running last year, on average, we're having 28 collisions each time you take the snapshot, each time you read out the detector. And you need to be able to disentangle all that. And a lot of what I'm involved with is the computing and software that actually does all this disentanglement. And you can see these spots here are identified separate collision points in one readout. And unfortunately, this is a Z boson going to 2 muons. Unfortunately, nature doesn't come color-coded like that, so you can't just see the yellow ones and say, oh, that's the one I want. It takes a lot of work to get there. Okay, but from quite early on, we were finding new stuff. Now, this wasn't the Higgs, but it is pretty interesting, and this is actually the first new particle discovered at the Large Hadron Collider. And I'm pleased to mention this one because it was found by my group in Lancaster along with the group in Birmingham, who basically the people I was doing my PhD with, so it's nice. It's a boson, but it's not a fundamental boson like the Higgs. It's actually something that's made up of quarks. It's made of a beauty quark bound with a beauty antiquark. And we know about that sort of state because they can be held together with the strong interaction. And in fact, we discovered a few of them before. So essentially, this peak here is one state, this peak here is another state, but this one had not been seen before, even though the theory of the strong interaction said it should be there and had predicted its existence 26 years before we observed it. So 28 years ago, people said that should be there. Other people had experiments which potentially could have seen it, they hadn't found it. It took ATLAS to be able to discover these things, so 30 years on. The other thing I like to say to anybody young in the audience is that analysis was driven by somebody who was in the second year of their PhD, so not much beyond where you're likely to be in your career now, and they were making, new particle discoveries at the Large Hadron Collider. You can get there, and it doesn't take, sort of an immense brain and everything else. It just requires a bit of enthusiasm and dedication, and you can do it. But now we'll come on to the pièce de résistance, because now I'm going to talk about the Higgs. So the main channel in which we discovered the Higgs was where the Higgs is decaying to 2 photons, so that gamma symbol I introduced before. You can detect those photons, not with those tracking detectors that we built in Lancaster, Liverpool, Manchester, whatever, but with the calorimeters that measure energies, because photons are not charged, so they don't leave tracks. But you can detect them, and what you do is you essentially take the 2 photons, you look at their energies, you look at the angle between them, and for actually probably year 13 physics students, you probably have enough relativity to show this, and certainly the undergraduates would be able to show this. If you want to look at the square of the mass of the object that's decaying, that's equal to twice the energy of the 2 photons multiplied together times 1 minus the cosine of the angle between them. It's really quite a simple formula. That's really what it comes down to. The trouble is, there are many things that can produce photons in the Large Hadron Collider. Many other processes can produce photons. And there's a lot of times where you'll have more than 1 photon in the event. So you take 1 photon, you match it with another photon, you can always generate something that looks like a mass squared, but unless it's coming from a single defined object, it will have a huge spread of results. In fact, it will have a spread of results that falls like that. But you give it long enough, we found that this pimple appeared on the distribution at one particular mass, at 126 GeV. That's the unit of mass that we use for our measurements in particle physics. And that turns out to be a really statistically significant excess above the background. If you want to play with this, we have a thing called a Lancaster particle physics package where you can play around with a sort of a toy Monte Carlo, toy sort of computer simulation of how you combine these things and how this sort of stuff works. Now, not only did we see it in decays to photons, we also saw it in decays of the Higgs to those massive analogues of the photon, the Z boson. In fact, one of them is not strictly on shell, but it's still decayed to 2 Zs. Now, this has different shaped backgrounds. There's lots of different contributions. So this combination of the purple and the red as a function of the different possible masses shows you what we would expect from all those background processes. What we actually observed is the spotted points, which you'll see, again, has an excess at 126 GeV. So in at least 2 different channels, and in fact a contribution from a 3rd channel, which is where you have the Higgs decaying to a W plus and a W minus, you started to see a signal coming through at the same mass in each case. So this really decayed in the sort of way you expect a Higgs to decay and had a consistent mass. Now here, I'm showing you why it took some time. This is the background building up, and I apologize for the cheesy music that you'll hear off my laptop. But this is the Higgs to ZZ signal building up over time. And you can see here, you're seeing something of an excess, but it's taking you, into 2012 before this thing becomes really significant. Okay, this is now going to zoom into the region of interest. So you can see the excess here where you subtract off the background. And this is what you would expect from the standard theory. So actually, you can also see from this that what we observed is a bit stronger than you might expect from the standard model. This is the backgrounds again, and slowly, you'll start to see the pimple evolving here. We're coming into 2012. We took a lot of data in the middle of 2012, and we start to get the excess. Okay, and again, you can plot that with your expectations and see how it works. But it takes a lot of time and effort to get these results. There were people who seem to think that we just turn on the LHC and we'd be announcing the Higgs that evening. It doesn't quite work like that. Okay, this is just a little bit for people who, if you're not familiar with statistics, you may hear people talking about, oh, and that's a 5.3 standard deviation signal, which actually is an incorrect statistical statement as well. If you take lots of measurements of the same thing statistically, what you normally get is this bell-shaped distribution of measurements. It's called a Gaussian curve. The expectation, the true value, if you like, would be sitting at the middle, and you have a spread around. And by definition, 68.27% of your measurements then fall either below or above 1 standard deviation of the true value. And if you go to more standard deviations, you can see 5 standard deviations. It's 600 in a billion of your observations would fall outside of that 5 standard deviation bound. And that's the gold standard for a discovery as far as most science is concerned. So that's the sort of thing we're talking about when we talk about the significance of our discovery. Now, what we actually said when we were saying that our discovery was beyond 5 sigma was, if all there is those backgrounds, then in fewer than 600 in a billion experiments, would you see a bump like the bump that we observed? So it's a 600 in a billion chance that we've got a fake signal. That's what we're saying. It's not actually a statement about the signal, it's a statement about a fluctuation of the background that might look like a signal. And that's quite an important distinction that some of the popular descriptions don't really get across, but it is quite important. And you can carry that bit of information across to many other statistical statements that people make in life. Often people confuse those two things. Okay. So this is our combined result. So these are all the possible different combinations of Higgs masses that there might have been. These are looking at the expectations that you would get from background or whatever and various bands, and this is where the signal sits. So this signal now is well above 6 standard deviations. It's nearer to 7. We took more data. We've also added in more significance. So all of that region is excluded, so you can see that there's only a little band there where the Higgs is allowed to live, and here you see something that really looks like a Higgs. Let's not go into the details on that one. So this really was the discovery of a new particle. We already had got to 5.9 standard deviations. So where do we go from that? Well, the idea of this thing is just the old cliche. If it walks like a duck and it quacks like a duck, it's probably a duck. But this plot, which I accept is really rather complicated, shows what you would expect a Higgs to decay into for all the different possible masses the Higgs might have had. So we now know that our Higgs mass is about here. So if you read off here, you can see all the things a Higgs might decay into. And this is a logarithmic scale, and this is saying, well, most of the time it'll decay into beauty quark and antiquark. That's fine. Here, it should decay into 2 gluons. Here, it should decay into 2 tau leptons. Here to 2 charms. And way, way down here, you've got its decay to 2 photons. And yet that was the strongest signal that we had. Now there's a reason for that, and that's because the backgrounds were easiest to understand for that particular channel. But what we need to establish is that all of these different branchings are correct. Because there are many other theories that would produce an object that look like the Higgs, but are not the Higgs. And there are many reasons why you would like one of those alternate theories to actually be what nature has chosen, because that can solve an awful lot of other problems that we might have. The Higgs actually could be one of a whole family of Higgses. Many theories say that there could be other Higgses, and the other Higgses would be less likely to be produced in the detector, so you have to take more data to be able to find those, and they'd have different masses. The other thing that we had to determine is whether this particle was supposed to have some rather odd properties. I mentioned the idea of spin before. Every fundamental particle we'd ever observed has a spin. Composite particles can be spinless, but fundamental particles have always had a spin. The Higgs was supposed to be spinless. So we very quickly were able to say that it was either spin 0, so spinless, or it could have a spin 2. You could tell just from the things it was decaying into that that was true. Decaying into 2 photons, it's obviously spin 0 or spin 2. What you can do is look at the angles between all the bits that the thing is decaying into and how it's oriented in the detector. And from that, we are now almost absolutely certain this is a spin 0 object. So that's interesting. It's the first fundamentally spinless object we've ever seen, which suggests that there really is this, what's called a scalar field, the Higgs field. And that's kind of interesting for a lot of other reasons, because the more recent cosmological result that you heard 2 weeks ago is associated with a theory which is driven by a fundamental scalar spinless field. Not the Higgs field, but something rather like it. So it's interesting that in the space of 2 years, maybe Victor has other opinions on this one, but there are 2, out of no scalar fields, suddenly we've got 2 that seem to have really important influences on the way that the universe works. So we're looking at trying to make sure that all of these branchings are right. We're looking for more Higgses, and we're looking to make sure that the thing's decaying the way it should. So I am concluding. I haven't got my timing right, good grief. We found something new at 126 JeV. We need to confirm it's responsible for the symmetry breaking. Something I haven't added to the slides was at the end of last year, what we'd seen was the thing was decaying into these things like Ws and photons and Zs. They're all the bosons. They're all the force carriers. At the end of last year, ATLAS, and including work from the Lancaster group who looks at this in particular, also showed that it was decaying into 2 tau leptons. So those, if you remember, were the bits, they were the matter particles. So we're showing that the Higgs is decaying in roughly the right way into at least one of the possible matter particles as well as the force-carrying particles. And it has to do that to be really the Higgs. And that's really good confirmation. But we need to check the rest of them. There may be a family of these things. And then the last thing I'd like to say is ATLAS is going to go on and investigate that, but there's plenty of other physics that we do in ATLAS. So one of the ones I'm really keen on and spend a lot of my time working on is a question of why we end up in a universe where there is you and me made of matter and photons, where in the early universe, with almost exact precision, you produce matter and antimatter in equal amounts. And yet somehow the antimatter has gone away and the matter remains. Now we know of at least one process which favors matter over antimatter, but nothing like enough. And so we are looking for subtle effects which might be evidence of what that process was that allowed the antimatter to decay away and leave a universe which had enough matter left that you and I could form. Okay, so that's one of the questions we work on. Another big question is this issue of dark matter, which, you know, I defer in a room full of astronomers and people doing astrophysics and cosmology to go too much into dark matter, but there's lots of experimental evidence that even potentially in this room, the majority of matter-like stuff isn't the stuff that we've been talking about. It's not the protons and neutrons and electrons. There's loads of other stuff. There's stuff called dark matter, and we don't know what it is. But we have lots of candidates, and potentially, just as we were doing in the early universe, you make all of the matter particles, we investigate the way the early universe worked. This dark matter was presumably created in the early universe. We can hope to make dark matter candidates directly in our collisions. We have various theories that will predict the sort of particles that might be. Well, we can also look at other quite cool stuff, like are there extra hidden dimensions? So we're off at the moment. We come back this time next year. We've doubled the energy of the machine. It's going up to its full design energy starting next March. It'll be either 13 or 14 TeV, so twice the energy we've looked at before. So new objects will be easier to find because we've got more of an energy probe range. But then we're increasing what we call the luminosity. We're putting more and more particles into the bunches. So you may wonder, why on earth do you live with collisions that were as messy as the thing I showed you before? Well, frankly, we're looking at stuff that's we're going to look at stuff 10 times as messy as that, we hope, within the next few years. Because the more things you look at, the more opportunity you have to find really rare events, the really rare processes where the new physics can be hiding. So we're increasing the luminosity and the energy to look for that. So it's a great time to be doing physics. Apart from the fact that, of course, everybody in the public sector gets flat cash and it becomes harder and harder to use what you've built. But frankly, having spent this much, it would be a bit silly to turn it off now, I think. And it's a really exciting time to be doing science for many, many reasons. And I wouldn't just say particle physics. The last words, I would think, would be, if you're young and you're interested, do get involved. And the other thing I'd say is the other exciting thing about science, I think, is the way that all of the fundamental bits of science, the cosmology, the astronomy, the particle physics, are all so closely linked and all influencing each other's discussions that this is a really good time, I think, to be looking at these sorts of questions. And at that point, I'll shut up.
Well, thank you very much, Roger. That was I found that absolutely mind-blowing. I don't know about you, but going all the way from rolling balls down a hill to blowing things up with liquid helium. It was only today I found out that actually happened on Roger's watch.
Oh, yes.
Really unlucky.
I was manipulating the computer.
You weren't the guy in there with the spanner when the doors came off. That's okay. So, time for questions. Do we have any questions for Roger? Yes. Can you just hang on a second, we bring you the microphone?
And I'm afraid I will repeat your question because we are being recorded and apparently they won't pick up the microphone very well. So
we'll give you a microphone.
I'm not being patronising, I'm just trying to help the recording.
Just two questions. You know, with the 11-dimensional theory, how does that sort of interact with Higgs interaction? And also with Brownian motion, would it be similar? Is that similar to the Higgs interaction as well?
Okay, let's do the two bits. I really have to think about that second one, actually. The first one, the first question was about how does all this fit together with 11-dimensional theories. So I mentioned these hidden extra dimensions. The reason why we have those theories, apart from the fact that the symmetries only seem to emerge naturally from a bigger theory which has that number of dimensions. There's a lot of ways, a lot of potential theories you can write down, but they don't break down into that U1 cross SU2 cross SU3. So that, though there are still rather large number that do. The reason you have these extra dimensions at some level is to try and give a unified description. So for instance, why is gravity so weak? Well, some of the ideas are that Gravity actually, again, is pretty much as strong as the other forces, but a lot of that gravity is acting through those extra dimensions, and so it's only the bit that's acting through the 3 that we normally deal with, or the 4 that we normally deal with, that you see the strength of that interaction. How would we observe it? Well, if you pump energy into the system, if you can pump energy into those dimensions, then you can do little things like, and you may remember the horror stories when we turned on, you can produce a micro black hole. Now that micro black hole should be no trouble to anyone. I mean, if we took all the energy of the beam, you'd make a black hole with a mass about the size of the smallest of the proteins in your body. And I don't notice many people being suddenly sucked into their own proteins. You will have to get very close to it to interact with it. And we also know that it should evaporate almost instantly. In fact, it would give a very characteristic signature in the detector. You'd see particles going out almost uniformly in all directions, large number of particles in a uniform way. How does that fit with the Higgs itself? I can't think of a direct, simple connection that I would put in there. Maybe on reflection I would think of something that did it. But potentially that Higgs field could actually be something which is not a fundamental thing. It could be an effective thing which could be generated by some of the features of these many-dimensional theories. So that's one way that it might play in. I don't know. Brownian motion, I'm not quite sure I see the connection. It's certainly as you go through Brownian motion, you're being jostled around by the things that surround you, and I can see that my party analogy might make you think in those lines. This is a little bit different. I mean, the other way that I could have explained it is you remember that energy is equivalent to a mass in relativity, that you take the energy is equivalent to a mass times the speed of light squared equals mc squared. The energy of that interaction with the field you can reinterpret as a mass, and that's really another way of thinking about what that interaction with the Higgs is about. I know I like the explanation actually that it's like going across a floor covered in treacle and it slows you down, but I know Peter Higgs hates that one, so I try not to do that as my main explanation and only introduce it later. So maybe not an entirely satisfactory answer to your question.
The other one I've heard, Roger, is if you've ever watched an international rugby match, and they always have an airship flying over the Millennium Stadium or Twickenham or wherever, and you get the shot down from the airship, and you can't really see very much. You certainly can't see the rugby ball, but you can more or less see the players when a scrum happens, and when the analogy is that the Higgs is the rugby ball that you can't quite see, but the scrums are the mass. I mean, all these analogies have their strengths and weaknesses. Any other questions?
But I might have known that the qualified county class referee would bring the rugby analogy into this.
Yeah, he's the referee who became. Yes?
Is there a limit?
Just a second till we give you the microphone. Thanks.
Is there a limit to the energy you can create in collision with these colliders?
Well, there's certainly practical limits. I mean, we're pushing the technologies now. The new collision energy should be what we call 14 tera-electron volts. That requires about the most intense magnets that superconducting magnets that you can make in large scale, because we need something like 1,200 of them around the ring. So you can make a more intense superconducting magnet, and you need the magnets to bend the charged particles so they go around in their circular orbit. Otherwise, you'd have to build an absolutely huge machine. I mean, if you give me enough money, I can build you almost any energy of collider. I mean, given enough money, I could build any energy of collider up to, almost the Planck scale. But, there probably isn't enough energy in the solar system for me to grab hold of. Yeah, I mean, it depends on your power source. It depends on the energy losses as well. So why do I say you need to have a bigger accelerator? Well, when you bend a charged particle, if you bend any charge, you're accelerating it. And if you accelerate a charge, it radiates energy. It radiates electromagnetic energy. So we have this problem with a thing called synchrotron radiation. As you bend it round in an arc, it actually radiates energy. And the tighter the arc, the more it radiates. So you want to have a fairly large accelerator so the energy loss through the synchrotron radiation is small. Some accelerators, like the synchrotron source they used to have down at Daresbury in Cheshire, And what, like the diamond light source they now have down in Oxfordshire, which was designed in Daresbury and then built in Rutherford Lab.
No more north-south jokes.
No, I didn't say anything. I didn't say anything. One of my PhD students runs the computing there. It's a wonderful thing. But that deliberately has a small arc because it wants to generate the synchrotron radiation, because the broad spectrum X-rays you get are actually really good for looking at the structures of proteins and crystal structures and things like that. So it's a good tool for other science. But if you want to get a lot of energy into your beams, you don't want it continually to be leaking away. That's also, if you like, I started off, as I said, with that accelerator, that tunnel, we used to have what was called a large electron-positron collider. That had electrons and anti-electrons, positrons, and collided those. Now that's a really clean way of accelerating, well, it's a really clean way of doing a collision because they're very simple objects. Protons are made up of bags of quarks held together with gluons. Am I allowed to use one rude word? Well, one rude word twice? Because Bert Richter, who was one of the leading sort of accelerator physicists in the US, described the sorts of machines like proton-proton machines as doing shit collisions. Because you're banging two bags of very complex stuff and all sorts flies out. Whereas an electron-positron...
Thank you for that mental image, Roger.
Electron-positron is two really clean, simple states which annihilate themselves. You've got all the quantum numbers are beautifully contained. The problem is the electrons are really light and the positrons have the same mass. So if you accelerate them in a given arc, they radiate a lot more than a heavier object. It depends on the mass of the object. Whereas the proton doesn't radiate as much synchrotron radiation. So in the same arc, I was colliding the electrons and positrons at 0.1 of a TeV, whereas I'm colliding the protons at currently 8 TeV, and we'll be colliding them at 14 TeV. So 0.1 up to 14 times the unit.
How fast is your night bus going when you switch it back on next year?
Well, it basically doubles the speed, so it'll be going at 400 kilometers an hour.
400 kilometers an hour.
Yeah. So possibly you feel a bit sick on the back seat, I suspect. So there's a lot of limiting factors, and that's one of them. I mean, there are certainly arguments that if you wanted to build a really big accelerator, it would make sense to plan to have a power generation station attached to the facility, because then when you're not running, you sell power back to the grid. And you don't have to then pay commercial rates for running these things. So people have seriously considered that sort of thing. But, you know, we live within the possible. There are plans for a very high energy machine which are on the drawing board, which would go, instead of just going round by the lake there, they'd go all the way down to Belgar, which is way down the valley and back, and be much, much bigger. That would go up to, the current plans are for 40 and possibly more tera-electron volts, but that would be a long way down the line. And there are people who plan to collide electrons and positrons. It's called the International Linear Collider. That's not got approval yet, but that tries to avoid the problem of you losing the energy by going around in an arc by firing them head on in a straight line, so you don't have the synchrotron radiation. The trouble is you only get one shot. The nice thing about a circular machine is you make these bunches, which are quite hard to do, and accelerate them to a high energy, but you can pass them through each other loads and loads of times. So what you gain in the energy, you lose in the number of things that you can record. It's a complex game.
Yes.
Good afternoon. My name is Ray Symes. I live in Cheshire. I was involved in particle physics many, many years ago. And my experience is that every particle you discover simply opens up a lot more questions than it really answers. And my question, therefore, is the discovery of the Higgs boson, is that generally seen in the particle physics fraternity as a closing down or a greater understanding of the structure of the nucleus, or is it simply opening up a raft of new questions? Because your last slide does pose a few fairly big questions still to be answered.
Those questions were there. Sorry, so basically is the discovery of the Higgs a closing of a chapter, is it opening of a new chapter? Well, I think it can be two, it could be both at the same time. And I agree with your general point that whenever you this is almost a general point about science. Each discovery usually opens up as many questions at least as it answers. I don't think it's an ending, because there are still so many open questions. It may close the chapter on certainly the question about the electromagnetic and the weak interaction. That if all you find is that one Higgs, that basically describes that part of the theory. And then you're left with the questions about the dark matter, the matter-antimatter annihilation, and so on. So the only electroweak questions are then asked about how the neutrinos interact, and that's actually one of the big priority areas as well. This thing called.
So you've closed the book on the standard model?
Not the standard model, because the standard model contains the strong interactions as well, and so there is still some questions there, but also, and I would argue that the matter-antimatter issues, well, they're potentially still in the standard model, but you almost certainly need to go beyond. So if it does close the book on the standard model, it tells you the standard model is incomplete, and it certainly has to have something added to it to explain these other things, which are not arising immediately because of discovering Higgs. I will be honest, I think actually in terms of science, it might have been more interesting for us to have found no sign of a Higgs at all, because then you truly falsify the theory. You have something that works beautifully and yet is fundamentally wrong. In some ways, that's more of a prompt for a revolution than a confirmation. But I mean, science proceeds by both. While it's true that philosophers may argue that science proceeds purely by falsification, actually the real practice of science is a mixture of confirming things and falsifying things. And I've got to say, it was quite nice to be there on the day of the, and I was actually down at the big conference where it was announced in Australia. I was in the VIP bit. I should have put that picture in. I was quite pleased. I was let loose on the press in the southern hemisphere after that. And also, we had a big collaboration meeting. We actually had a collaboration meeting in Marrakesh when they announced the Nobel Prize. That was a great day. So in that sense, I'm pleased that we found the Higgs, and it's nice that we did close the book. But there's part of me as a scientist that actually also thinks that it would have been almost more interesting if you'd really broken the thing.
Remind me not to loan you my car, Rog. Any other questions? Yes.
I apologise if this is a very naive question because your lecture is very stimulating. I hope I didn't miss anything. But what I wanted to know is you sort of glossed over the fact that you seem to be able to predict the decomposition of the Higgs boson before it was actually detected. So how are we able to predict what its decomposition products are?
Well,
you mean without knowing its mass?
Yes.
Well, yes.
Yeah, no, that's actually, that's an interesting question. It's because for the Higgs to be describing the masses of those fundamental particles, you know the way it does that is by its interaction. So you know its interaction strength for each of those different particle types. And that interaction strength also tells you the rate at which the thing should decay into those particle types. So it's tied to the fact they're explaining the masses of those particles. The problem is, in the absence of seeing a Higgs, the Higgs is generating its own mass. The Higgs couples to itself to generate the mass of the Higgs. And until you knew its mass, you didn't know the strength of the Higgs self-interaction. And one of the big things for the future, actually exploring the whole physics of the Higgs, I mean, that is definitely a program you need to do, just to come back to the previous. You need to really check out all of the properties of the Higgs. And it's not easy to do. The Higgs self-coupling, for instance, certainly requires a higher energy and higher luminosity collider than we had so far. Yeah, so I've slightly lost my thread there, but this self-interaction required you to know the mass of the Higgs. Sorry, I probably was about to say something else and I've forgotten it.
Did anybody figure out why it was inclined at a degree, by the way?
Yes.
I have a guess, but sorry?
Yeah, my guess is that the effect of gravity
It's an interesting guess, but it's not the answer. It's a really practical answer.
Of the Earth?
Hand at the back.
Was it to move the detectors?
Sorry?
When they were building the collider, was it to move the detectors into place?
No, that's another good answer.
It would have ended up above ground if you hadn't put the incline.
No. It's only a 1 degree, and this thing's going from a. This thing's we can do our geometry. It's going from 50 metres underground to 150 metres underground. I don't think 1 degree is going to make a difference.
Is it due to the curvature of the Earth to counterbalance that?
No, it's not.
That was my guess.
Yep.
You thought you were wrong, yeah. Don.
It's underground and it leaks and you need to drain the water.
That's half of the answer. Very good. It's because of the water. Well, there's two things. First of all, you would want to do the civil engineering that way a little bit because the natural strata are actually running at an angle, and you don't want, there were some harder rocks it would have been hard to go through. But then it was realized it was a really practical reason for this as well. You are 150 down to 50 meters underground. There are underground watercourses. They cut through an underground watercourse when they made this tunnel in the first place. Had to pump loads and loads of concrete in to seal it all up. So this thing does leak, and you need to drain it. If you didn't have it as an incline, the water would pool. If you do have it on an incline, you can drain it and you can pump it out from 1 or 2 places. It's truly practical civil engineering. It is. Well, when you think that you went with this thing is 27 kilometers round, when they actually met up, they met up within about that level of precision. And they're doing this underground, completely in the rock. I mean, it's an astonishing piece of geodesy, as they would call it in French.
When the two halves of the Channel Tunnel met,
yeah.
They took that, but this is even cleverer.
Well, we'd already given them the technology for that. I mean, essentially, it was done earlier. No, I mean, it was done earlier. This sort of, I don't want to do the whole CERN drives lots of impact thing, but it is true. You'd be surprised the practical things that come as spin-off out of. I believe there was
not
some.
Just the internet.
I believe that. Well, I believe there was something called the web.
We have arguments about this. The astronomers got there first with a thing called Starlink.
That's just
a debate for in the
That's just
Are there any final questions?
Internet protocol, not the same thing.
We'll take one from the back, because we haven't been to the back yet.
Hi. With regard to the question of where did the antimatter go?
Yeah.
It seems to me you could regard that in a very simplistic way. You were saying that it should have been created in equal parts matter and antimatter in the early universe. It seems to me you could regard that in a very simplistic way as a breaking symmetry.
Yeah.
With and now we have all this matter and very little antimatter.
Yeah, there's a big symmetry breaking.
Is there any school of thought or any reason to believe that breaking of symmetry with regard to matter and antimatter is somehow linked to the breaking of symmetry in the electroweak force and therefore linked to the Higgs mechanism?
Well, there is part of the weak interaction that does prefer matter over antimatter. It's called CP violation, is this general process. And we can measure that. And it's been known for quite a long time. The problem is it's about 1/10,000,000th the amount that you need to account for the asymmetry we see in the universe, which kind of suggests that there's some other process there which has also got a much bigger CP violation in it. Now, maybe it's not. Maybe there is something hidden in the standard model, and I don't do the theory calculations, but maybe there is something that amplifies these effects that somebody hasn't thought of. I'm a plumber at the end. We have a mutual friend called Simon Hans who works at Swansea. He used to go to school with me, and he refers to me as, oh, Roger, he's a plumber, because he does the theory and I do the measurements. And it's true, I'm proud to be a plumber, because at the end of the day, it's the data, it's experiment that tells you what nature's done. Though it's nice to be guided by some smart ideas, at the end of the day, it's the experiment that's the arbiter. So, yeah. It's an interesting line of thought that you have. There is a connection there with the electroweak sector.
I think on that absolutely profound note, I think we should wrap up the formal part of the afternoon. Please don't feel free that you have to charge away. Roger will be around for the rest of the afternoon if you want to carry on talking to him. But for now, let's just thank Roger again.
I've got another half an hour actually.